All right, good morning, everybody, and thanks for the organizers, of course, for putting up this fabulous meeting and having me as an outsider participate. I would like to talk about an old problem, spin glasses, and in fact, it's such an old problem that I'm not quite sure that everybody knows what it is, and so I want to spend a few minutes to explain it. Actually, I always thought that this is, the term itself is quite unique, and you couldn't mistake it for somebody else, but then recently I found out about this. So apparently there are some people which think that spin glasses are something else. So that's obviously not the type of spin glasses I will be talking about. So the classic type of system that one means by spin glasses is a set of magnetic ions that are dispersed in a non-magnetic metallic matrix, and the interactions between these are such that they can have, depending on the distance, ferromagnetic or antiferromagnetic nature. And that combination of frustration and disorder together creates the spin glassy type of behavior. So in practice, we very often look at simplified models like the Edwards-Anderson model, which is essentially an Ising model on a lattice, which has couplings which are quenched random variables, which can be positive or negative. And so the point of my presentation here is to talk about different coupling distributions. So these Jijs, they could be, for example, from a continuous distribution like a Gaussian, or from a discrete distribution. There's been a discussion in the community about whether this makes a difference for the critical behavior. So obviously there are some differences. I mean, if you have discrete distribution, there will be an energy gap in the spectrum, and that might make some difference, whereas this is not the case for the Gaussian distribution. And so if you look at some of the critical exponents, you see that they are different. They appear to be different, I should rather say, between these two models. And so that's kind of the focus of what I want to talk about. One other obvious difference between these models is that for the discrete distribution, you have a degenerate ground state. So there's actually a large number of ground states kind of depicted for a small system here for the discrete coupling case. And in fact, you can show that there is a finite residual ground state entropy. So there's an exponentially large number of ground states in that system. And so that might make a big difference. The general phase diagram looks like this. So P is the fraction of antiferromagnetic bonds, and T is temperature. So for sufficiently large frustration, let's say, and low enough temperature, you expect a spin glass phase in that system. So that's the generic case. But in 2 dimensions, it turns out that there should not be spin glass at finite temperatures, only at 0 temperature. And so that's the phase diagram here on the right. So that's, I want to talk about 2 cases, the 2D case first, which is shown here on the right-hand side. And so the type of approach, I mean, obviously, if there's spin glass only at 0 temperature, we better look at 0 temperature if you want to learn something about spin glass in that specific system. And there are clear differences between the 2 coupling distributions at 0 temperature. So there are some of the critical exponents, like the so-called spin stiffness exponent, which I will comment on a little bit later on, which are different. And so what we're trying to do is really to determine ground states for sufficiently large systems, because there's strong finite size corrections in that problem. And so I will not have time to actually explain the method, but it's based on essentially representing it as a minimum weight perfect matching problem, so a problem that is known in theoretical computer science, and that allows us to look at large system sizes. We also have some tricks for making it work, because traditionally this only works for planar graphs, but we can now make it work also for graphs which have fully periodic boundary conditions, which have smaller finite size corrections. And like this, we can actually go to quite large system sizes. So this is something like 10,000 squared, and this is the system size that could previously be done. So it's a significant increase in size as it can be treated. What are we looking at? I mean, one of the quantities is this spin stiffness exponent. That's very similar to what you would look at in a ferromagnet when you say, okay, I have an ordered phase, now I have a droplet of the opposite sign. What's the energy contained in that droplet excitation? Obviously, that's contained in the interface. So the scaling would be L to the d-1, so the size of the interface. In the spin glass, that's a little bit more complicated. So the d-1 is replaced by an exponent, which is called the spin stiffness exponent, which is one of the essential quantities in this problem. And so the results we find, I mean, we can really take a lot of scaling corrections into account, and then, for example, determine the asymptotic ground state energy very accurately, and also the spin stiffness exponent, which I just mentioned. So that is turns out to be this value. It's negative, confirming that there should be spin glass only at 0 temperature. And also you saw that these domain walls are fractal structures, so we can expect that there's a fractal dimension, and we can determine that also with very high accuracy. If we do all of that for different boundary conditions, we get consistency. Interestingly, there was a suggestion, a conjecture by Mike Moore and co-workers from a while ago that relates the fractal dimension of domain walls to the spin stiffness exponent based on SLE and conformal field theory. And it turns out that our results are now accurate enough to actually see that this conjecture is likely not correct because there is no consistency with our numerical results. Then we can also look at the bimodal case where you have degenerate ground states. There you have to think of how do you make sure that you sample the ground states uniformly, because only then do you get thermodynamically accurate results. We have certain algorithms for that. The spin stiffness exponent is 0 in that case. And we can actually also determine these domain wall fractal dimensions. There are 2 different definitions, but they give consistent results, and they are also at least marginally consistent with what we find for the Gaussian case. So now let me, in the last few minutes, say something about the more general case, including 3 dimensions where you could have spin glass, or you in general you would have spin glass at finite temperatures. You saw that there are some differences between the discrete coupling and the continuous coupling cases, so it seems desirable to somehow connect these 2 cases in some way to understand more generally what are the differences and common points. And so we try to set up a model that has a tunable degeneracy, so where you can have as a function of a tunable parameter one limit where there are degeneracies and another limit where there are no degeneracies, and that can be done using layers. So imagine you have on each bond several of these ±1 couplings, and then you just sum them up. So for example, for 4 couplings, you could have these realizations, and then you see, well, this is something like a binomial distribution of the couplings. We just take a rescaling factor here into account to make them go to a finite limit for a large number of layers, so m is the number of layers here. And you see that because of that binomial, if you send m to infinity, that approximates or converges to a Gaussian distribution, so that includes the Gaussian limit, whereas if you have m equals 1, that's just the standard bimodal case. So we have connected the 2 models, and then we can do some rigorous mathematical analysis on this model, and in fact we can show an upper bound, a rigorous upper bound, which is independent of the graph structure, for the ground state entropy, which is shown here. And you see that if you send m to infinity, that bound will contract. And in fact, we can show that there's a unique ground state pair in that limit, in the Gaussian limit of m going to infinity. Whereas, interestingly, if you have a certain correlated limit where you keep n divided by square root of m fixed, you can have degeneracies in the system. And so you see things depend on how you take the order of limits in that specific model. So, and then we also did some numerics for the square lattice again. So this is the ground state entropy as a function of square root of m, and it turns out that this was just an upper bound. It didn't say anything about the actual scaling form, but the actual scaling form really follows that functional dependency as is shown here. So these are the fit forms, which are exactly the form also of the upper bound. And then you can wonder, for example, I showed you that the spin stiffness exponent was about -0.3 for the case of the Gaussian distribution, and it was 0 for the bimodal distribution. How does that go together? So you can plot the defect energies as a function of L for different numbers of layers, and you see that there is, the Gaussian case is approximated for m large, but for m small, things seem to settle down. And so you could define an effective spin stiffness exponent, which would seem to interpolate between -0.3 and 0, but this is really only an effective view. So we expect, in fact, that there is a crossover length, and we can show how that should scale. It should scale like m to the power of -1/2 theta, where theta is the spin stiffness exponent, such that if you're below that crossover length, you actually look like you are in a continuous system, and only beyond that you see the discreteness of the coupling distribution in that case. And so that brings me to the conclusion of my talk. 2 things: we can really determine these ground state properties very accurately using matching algorithms, seeing differences between the continuous and the discrete distributions, and more generally independent of the lattice structure, we can come up with a model which we think has some potential for future analysis, which connects the two types of distributions. So, and then there are some references down here if you want to know more about them. Thank you very much. I'm open for questions.
Questions?
In the random field case, if we take a trimodal distribution, then it turns out that the phase diagram is more like a Gaussian distribution in that case. Trimodal is still discrete. So is the difference only of discrete or continuous here, or?
No, yes. I mean, it's a good point. It depends if you have several discrete peaks, more than two. Then it depends really on whether they are at commensurate locations or not, right? I mean, if they are at some kind of irrational, relatively irrational locations, then if you sum them up, you essentially create a continuum, right? And so it's really only in that case where you have discrete points which remain discrete even if you sum them, that you would see different behavior.
So trimodal will still be discrete.
It depends on where you put the for example, if you have one at 0 and one at plus minus 1 or something, that would still have this discrete behavior, I think.
Okay. And one more, what is the kappa for the SLE for the random bond case?
I think it's about 2.8 or something like that. It's not a rational number. I mean, this is you can't really directly map it. It's a numerical determination of the kappa of the SLE, and that comes out as 2.8. I mean, it could be, of course, a fractional number if you just choose, sufficiently large numerator and denominator, but it's not known. I mean, there is no. It's purely a numerical result.
So, in the just a clarification. In the let's say when you find this the length of the clusters, this is in the spin glass phase, is it?
It's in the spin glass.
So how do you identify what the domains really? I mean,
right. That's a good point. Yeah. So the domains, I didn't explain that. The domains are in overlap space, right? So you compare two configurations, which in themselves they look completely disordered, obviously. So they are just different by different boundary conditions. So you try to induce an excitation by changing from periodic to anti-periodic boundary conditions. And then you look at the overlap of these configurations, and in some part they will have the same relatively the same configuration, some other part relatively the opposite configuration. So you have a domain wall separating these two.
Okay, so let's thank Martin again.